Okay, so we've got two disks with the same radius r. They're free to rotate about some common axle with negligible friction as shown in the figure above. I forgot to draw the figure, but it basically looks like here's our disk. And then through it, we've got this little, this axle, and the axle also extends out this way. Yeah, all right. I forgot to draw it, but there it is. They're free to draw about a rotate about a common axle with negligible friction, as shown in the figure above. One disk with a mass m, so that's our first disk, okay, is initially spinning freely with an angular speed m0. I don't like that they used m0. Normally we use m for mass. Normally we would say something like p0, I think. I think that's the common convention, but that's unrelated. All right, angular speed m0. The other, with a mass 2m, okay, is at rest. The rotating disk is then moved against the stationary disk, and friction gradually causes the disks to rotate together. So we have this larger disk, right? And originally it's not spinning, but then we start to push it this way until they connect. And now it's one giant disk. Okay? Moved against the stationary disk, and friction gradually causes the disks to rotate together. So since they're together, we should expect the same momentum. Okay? What will be the final angular momentum of the disk of mass 2m? So specifically this angular momentum, not the of the total system, right? Okay. So let's break down a couple things. Number one, let's first think about what I need, or what my answer will be. My answer is going to be a momentum, angular momentum. So it's going to be what we call omega. And we're going to say this is the mass for 2m. So the angular momentum of this disk that's 2m big. And here this will get me thinking about, in my reference sheet, what do I need, right? And then we think about what we have, the information we have. Well, we have that we have one disk, right? We have this disk. This one has a mass of m and a radius of r. And it's got some angular speed m0. This is the omega 0. Yeah, omega 0. Okay. And then what do we need? We need to go from here, to go from all this information to here, right? I'm going to need the total inertia, rotational inertia, or my total angular speed, right? Maybe I need my total angular speed, or maybe I need my total momentum, right? My total momentum. We'll use a capital L for that. All right, so with that in mind, let's first think about what is our initial inertia, or our initial momentum. So we're going to use 0 to show that times 0. This is our initial momentum. We need I of the initial thing, right, our starting point, times the starting speed, okay? For a cylinder, since this is a disk, which is basically a cylinder, right, this, for a disk, is going to be equal to 1/2 times whatever the mass is times the radius squared. Okay. They don't give us numbers, but they do give us these variables. So here, when I think about this, it's going to be 1/2 times the mass times capital M times our radius capital R squared, right? And then when I think about my rotational speed, right, it says freely with an angular speed m0, that's the initial point. So it's equal to m0. Again, I don't like that they use m0 instead of like omega 0, but whatever. Okay. So now that we have this, we can say that our initial momentum is going to be 1/2 times m times r squared times m0. So again, they don't give us any numbers, so this is what we're going to be working with. All right. Now, for our final, right, we need our final momentum. We need the inertia of the final system times the angular speed of the final system, right? And I know that this is going to be equal to our initial momentum because we have conservation of momentum. So we have conservation of something moving and then hitting another ball, and then that gets knocked around, right? We also have conservation of angular momentum, right? So if it's spinning, unless we have air resistance, unless we have drag, unless we have, my hand, right? My hand pushing on this and stopping it, causing some friction, we know that we're going to have conservation of that momentum, right? So let's go ahead and erase all that. Okay. So let's figure out, what is this? They don't give us many clues as to this, right? Because that's what we're looking for. That's what we're eventually trying to get. Well, not eventually. This is the second to final step. But we first need to figure out, what is our final system? Well, similarly to how we can add, like if I have a block and this is mass, and then I have another block and this is mass 2, I can just add m1 plus m2, right? That's how I can do it normally, with what's called translational physics. I don't know. Anyway, but if I have rotation, right, and this has some inertia, I can actually add my inertias together. I can do what's called a sum of my inertias, right? Okay, so what I'm going to do is I'm going to add all my inertias, all i's. Okay, so first let's figure out, we have the initial one plus the one that has a mass of 2m, right? That's our second disk that we talked about. It's going to be a bigger disk, right? And it's going to be connected. Okay. So this one we already got. We got that one from here. So let's go ahead and plug that into here. Okay. So we've got 1/2 times m times r squared. Okay. As for this one, it's also a disk. So it follows the same formula, but the only thing that's different is our mass is different. And then our radius, they said it was the same. So we have r squared. Right? If we look over here, it says they have the same radius, r. Okay. And so that's going to be our final, or our total rotational inertia. And then I'll just do some algebra over here. I noticed that 1/2, this term is the same as this part, right? So what I can do is I can say this is 1/2 times m times r squared, and that's all times 1 plus 2, right? Because this is one piece of it, and this is two pieces of that. Again, this is just kind of algebra practice. If this is where you're, let's put a star here. If this is where you're messing up, then we're going to need to practice, trying to simplify algebraic expressions. All right, so now we've got 3/2 m r squared. Okay, and this is our total. We're going to rename this to total. Final takes too long to write, so don't worry about that. This is now called our total rotational inertia. And remember, this has to be, right? Once we find the rotational inertia, I can plug that into here, find the final momentum, and the final momentum has to be equal to the initial momentum, unless we have heat loss, unless we have, some other loss, that's some energy that's leaving the system. So what we've got to do is we've got to figure out, so we have our I total times our total angular momentum, and that's going to be equal to, well, what did we say this was? We said that this was this whole section right here, right? That's this whole section. So it was 1/2 times the mass of the first disk times its radius squared times our initial angular speed. Okay. So this is where we're at. Now I can go ahead and plug this section in right here. So we can say that that is 3/2 times the mass times the radius squared. Notice how it started off as 1/2, but now we have 3 times as heavy of a disk compared to before, because we don't just have the original disk, we don't just have the new disk, we have both disks added together, and so it's 3 m's total. All right, that's going to be times our final, or our total rotational speed. And then we've got, that's equal to 1/2 m r squared times m0. All right, so this is, again, more algebra. If you are struggling with this step, then that's going to lead into, we need to practice with solving for variables, okay, when we don't have any numbers. All right, so I'm looking for this variable, right? That's what we're trying to figure out, this variable right here. And so let's look at what we have in common on both sides. We have the m's, we have the r squared, we have the 1/2, right? And so now we've got 3 times our final angular velocity is equal to the initial, right? So this is telling me that the initial velocity, when we have just one disk, is 3 times faster than once we add both disks together. Okay, so we can also write this as 1/3 of our initial. And I think that makes sense, right? So if we think about our disk, we think about one disk, and then we have another disk, a disk that's twice as big as it, right? We're essentially splitting this up into, so this right here is 2 pieces of it, and this right here is 1 piece of it. And so we're kind of splitting it up. It's 3 times heavier, so it should be 3 times slower, right? Something like that. So I think this seems to track. And so this was actually what I originally put as my final answer. But let's go back and let's remember what the question is actually asking. It's asking for the final angular momentum. So we're looking for momentum, not the speed, of the disk of mass 2m, right? So not of the total system, but of the disk of mass 2m. So we're looking for this, the momentum of the disk of mass 2m. That's going to be the inertia of that disk times how fast is it going, right? Well, we just figured out how fast it's going. It's going this fast. It's going 1/3 as fast as the original. So now I need to figure out this one. Again, we have a cylinder. So this is going to be 1/2 times the mass of that disk, or that cylinder, times the radius squared. And so this is going to be equal to 1/2 times 2m times the radius squared times 1/3 times the initial velocity, the initial angular velocity. Let's do some more algebraic simplification. This is another step that we're just going to kind of push through for the sake of time. 1/2 and 2, those cancel out. Nothing else cancels out. So what we'll end up with is 1/3 times the original mass times the radius squared times the initial angular velocity, and that's equal to the angular, the rotational velocity, and this is the rotational momentum of that second disk. Okay, and so remember, it's not of the full system. We're only looking at this one. We're only looking at that one. Okay, hope that helps.